First part we're set with. Alrighty. Well, welcome to the public portion of my talk. As you can probably tell from the title, it does involve two different segments. I studied both interstellar clouds in our galaxy, the Milky Way, and then also Astro 101 students as well. And so that had to be mixed together in some interesting way, and it worked for me. But I'd like to say thank you to both of my advisors, Yancey Shirley and Ed Prather, for getting me to this point and helping me with all of the work and guiding me along the way. So thank you very much. I would also like to say thank you to all of the co-authors on my papers. Many are at Colorado and all over the rest of the United States. Some are undergraduates and other graduate students, and without them and their guidance and sometimes their data and other work, much of the work in these papers would have been thousands of more hours from what we were trying to do. So building on the knowledge that they had and then applying their information in new ways was tremendous. So I've broken the talk into two pieces. We're going to have a star formation section to begin with, and then there'll be sort of a short break as we go into the second part. And the second part will definitely be more interactive from the first, but you will need to learn something from the first part of the talk because you'll be tested on it. But to begin with, we will go over a quick primer of the electromagnetic spectrum, because I know everybody in this room is not necessarily an astronomer or has not necessarily used it in a very long time. So the electromagnetic spectrum is a fancy name for light. There are many different colors of light beyond those that we see in the visible spectrum, but you can learn different things about astronomy, about the universe, by studying these different types of light. If you want to study high energy objects, so neutron stars, black holes, you might use ultraviolet, X-ray, and gamma rays. If you want to study where all the gas clouds are, or cold objects in the universe, you're going to want to use radio and microwaves. And as you increase in energy, you increase in frequency, and you decrease the wavelength of light. So for most of my observations, we were using millimeter wavelengths of light. So about this big were the photons for much of our observations, and that means they are low frequency, fairly low energy. So we need very big telescopes in order to collect enough information in order to detect them. Now, this is a multi-wavelength image of our Milky Way. So the galaxy is spread out across the center, and the plane of the galaxy is in the middle. And you can see in gamma rays, there seems to be a lot of very bright objects, like the center of the galaxy. Well, that's the black hole at the center of our galaxy. There's other bright objects, and those might be stellar mass black holes or neutron stars. Same with X-rays. There's a lot of very discrete points, and it shows up as very hot gas. If we look at sort of what we would normally see in the night sky, in the optical, you see that dark band across the sky. Well, that's all the gas and dust that is going to eventually form stars in our galaxy, and that's what we're looking at when we're trying to study a star formation. You can see there's a couple areas where, oh, it's red. That's where stars are forming. That's where we have heated up that gas and dust, and the hydrogen is glowing because these big stars are warming all of that up and causing that hydrogen to emit in very specific wavelengths. But if we move to slightly longer wavelengths into the near infrared, we can get rid of all of that dust. Once the wavelength of light is longer than that dust particle is big, it basically becomes invisible. And so you can see that there's a little bit here, but for the most part, you can see all the stars in the galaxy. So as you move through these different wavelengths, you learn different things about the galaxy that you live in. The mid-infrared. The mid-infrared is looking at the hot dust that is an active component in forming stars. There is a lot of emission coming from all the star-forming regions in our galaxy. And so this is sort of that total amount of that emission. You can see where all of the warm dust is in our galaxy, and it forms that nice band towards the center. If you go to farther, you're now looking at colder dust, and you can see that the dust is getting farther away from that midplane. This is stuff that's closer to us. And so now we're looking at these big star-forming regions that are close and taking up huge chunks of the sky. And that's the cold dust that has not yet collapsed into these regions that are starting to gravitationally collapse and warm back up again. But we're looking at the coldest, more of the coldest dust. And then the next step would be to look at molecular hydrogen, or in this case, this is the carbon monoxide map of the galaxy. Carbon monoxide traces all of molecular hydrogen, which has to be cold and fairly dense in order for everything to form. And so this is showing you basically all of the giant molecular clouds of which everything starts with the star formation process. And this is very similar in structure to that cold dust, but very different from the atomic hydrogen, which is, there's just so much of it that you can't tell much structure from it. So in order to understand these various things, we want to study stuff that traces molecular gas. And one last thing before we move on is a black body spectrum. Any object that is opaque and has a temperature will emit a spectrum of light that is this shape. And that temperature tells you what its peak wavelength is. Now the objects that we're looking at peak out here at 1 millimeter. So they're not 100 Kelvin, they're down here closer to 10 Kelvin, 20 Kelvin. So we're looking at very cold things when we're looking at radio wavelengths. So now to introduce the first part of the survey that we joined, the Bolacam Galactic Plane Survey. It is a 1 millimeter dust continuum survey. So we're looking at the coldest dust. And this dust takes a fair amount of, it has to be fairly dense before we can start to detect it. So we're going to see not this diffuse emission, but we see nodules. And so the Bolacam Galactic Plane Survey basically observed everything that's within the white in the first two panels, and then all of the black outlines in here, which ends up being about 140 some square degrees of our galaxy, looking at that plane of the galaxy. And the reason we look at the plane of the galaxy is because, as you saw in all those previous images, the galaxy is very flat, and most of the material happens to be right near that galactic midplane. So that's where this survey was focused. Now, if we look towards the galactic center, this is a sample region from the newest maps from the BGPS, the Galactic Plane Survey, and we're tracing very cold dust, and every red ellipse is an individual BGPS source. So if we were to do this region with our follow-up survey, we would have to point at every single one of these. And so there's probably a good 300 sources in this just small chunk of the sky. This is half degree in galactic coordinates by a half a degree in galactic coordinates. So it's not a very large region of the sky. Now, we're looking at stuff, we need to find a tracer that looks at the densest gas. And those in the back, feel free to come in, find a seat. We want something that traces something that's denser than what it takes to light up CO. CO, if you look across the galaxy, will have multiple velocity components, because it doesn't take much to make CO excite. And that's why it's such a great tracer for where all the molecular gas is. But if we're looking at these dense dust clumps, then we want a dense gas tracer that traces a density that's appropriate for those dust clumps. And one of these dense gas tracers was HCO+. And an example, you can see that it only shows up over on that last peak. Well, when we're looking at these different dust clumps and we see one, it's most likely that that dust clump is going to be associated with that last peak and not the rest of this gas that we see in the middle. So we performed spectroscopic follow-up using the submillimeter telescope on Mount Graham. We used their 1 millimeter ALMA receiver, so it was good practice for a lot of the ALMA work that is to be done in the future. We were able to get a 55 millikelvin baseline noise level, which is actually really small if you think about the fact that we integrate for 2 minutes. And that's because this generation of receivers is just that sensitive. So this would not have been able to be done 10 years ago. We had to find designated off positions, so areas of the sky that were clear for every half a degree in galactic coordinates. So for every patch that we were looking at, like that first one that we just saw, we have to go find a clear area in there and find that for every single patch of sky that we look at. Then we also have to calibrate and point each hour for the telescope, so we're getting at least 15 sources per hour. We ended up observing nearly 2,000 sources by the time we were done in HCO+ and N2H+. And we've chosen both of these dense gas tracers because they have similar effective densities as each other, similar effective density to the dust, so they all light up in about the same physical conditions. And when it comes to the chemistry of these molecules, they react oppositely to carbon monoxide. N2H+ is destroyed by carbon monoxide. So if you don't see a lot of it, it may indicate that the cloud's a little bit warmer. Versus when you see it, you know that the clouds have to be fairly cold and the CO has to be frozen out. Whereas HCO+, since it has CO in it, has to be created from carbon monoxide. And so those ratios can give you an indication of chemical timescales that are happening within some of these sources. So here's some examples from the data from our spectroscopic survey. We had to flag all of our data because not in all in all cases you don't just get this beautiful line that's Gaussian in shape, exactly what you'd want to get. But sometimes, other than having this, what we'd call the sort of the ideal situation, we might have something that has two different velocity components. Well, what clump does that associated with? We can't tell, and so that means that we have to sort of throw it out at this time. Also, some of these sources are very active, and they may have line wings because gas is outflowing. So whenever gas is moving, you have a Doppler shift, and that's why we have a velocity on this bottom axis. When something's moving towards you, its frequency is shifted to higher frequencies, higher energy, shorter wavelengths, and we'll have a negative velocity. So if stuff is moving towards us, like this one is, it's going to be slightly to the left of 0, whereas stuff that's moving away from us will have a positive velocity. And that is what gives us our blue shift and red shift. And we use that to, one, understand the kinematics of our own galaxy, but also later to determine other properties about these sources. So in addition to line wings, the last set of flags that we'd have would be for what we call self-absorption. In the case where the gas in the center of this clump, of whatever it is so cold and dense that the light from the other side of the clump can't make it all the way through. And it actually starts absorbing itself. So instead of just an emission line, you now have an absorption line in the middle of your emission line. So with 2,000 sources, you actually get to start to do statistics about stuff that you can find. And while we looked at primarily the brighter sources in the BGPS catalog, we also had a large chunk of sources that were selected from all flux bins. So we were able to sort of get average statistics about what you'd expect from sources when you go out to look for them. And we're able to detect nearly 80% of sources in HCO+. So that's pretty awesome. It means we can get a lot of information out of that. And about 60% of those were those nice signal detections, which makes it really simple to analyze. With N2H+, we ended up detecting about half. So about half of the clumps out there have large reservoirs of very cold gas, which you would need before you start collapsing to form stars. So with that VLSR, or the velocity with respect to the line of sight from where you're standing, you can tell whether things are either moving away from you or moving towards you. Now, this map right here is a map of the galactic rotation curve, basically, from where we would view it from Earth. So the map itself is from a CO survey from Dame et al. And what they did was they mapped the entire galaxy in carbon monoxide and plotted up their basically position versus velocity diagram. Now I've plotted blue data points across all the places where we've detected things. And what's nice is that all of our data points seem to line up on top of where the brightest CO is. So we're looking at areas that also have a large reservoirs of gas, which is what you need to form stars. We also don't have any data points that are outside the galactic envelope, which is a good test to make sure that we're sane in a lot of the things that we're detecting. But with that VLSR, the first thing that you can do is compute a galactocentric distance. With the velocity and a model of the galaxy, we can then say, like, well, okay, so if we're sitting here and we see a cloud here at all these different locations, and this is how the galaxy works, I can tell you where it is. And so the first thing you can do is say, okay, well, where are all the sources in the galaxy? And you can see the different galactic structures as you move away. You can see the outer Perseus arm that's outside of us. You can see the local arm, and a lot of these clouds are in the Cygnus region. The Sagittarius arm internal of us, and also the end of the bar, the galactic bar, because we're a barred spiral galaxy, and there's also a ring of molecular gas that exists right around that same radius. And so we're able to see all of that just in starting to do this, look at statistics from our data. Now, okay, it doesn't show up real great, but the next thing that we did was we want to break the fact that from a galactocentric distance, you just know how far from the galactic center you are. You could be on this side or this side of the galaxy. We don't know which unless there's some way of measuring the exact distance to any of these clouds. So what we did was said, there's these objects called infrared dark clouds, or IRDCs, and they are dark against the background of infrared light that's coming from the whole galaxy. Well, if they're dark against that background, it means they can't be very far away, or the background would be in front of that cloud. So we can assume that those are all on the near side of the galaxy, or closer to us than many of the objects would have to be on the far side. So we can use that, and that's why there's all these objects down here on the near side of the galaxy. We can also use known distances. So if somebody has measured the parallax distance using a VLBA network to measure the exact trigonometric distance to an object, we can plot those out here, and that's what some of these farther ones are. And also, some of these velocities that are all the way out here only correspond to this side of the galaxy, and that's why those objects were also selected to be known distances. The distance ambiguity also doesn't exist in the outer part of the galaxy because there's no other side of the galaxy to look at. So it makes it very easy to determine these out here. And so with these velocities, we were able to break this distance ambiguity for nearly half of our sources. And that's why you can start to see galactic structure outside the galactic center. You can start to see the molecular ring and the Sagittarius arm. And then the local arm would come right here because the sun is here. And then the Perseus arm comes around outside. But once you have distances, you can now take information that you've gleaned from either the spectra or from these BGPS maps, and we can turn these into masses. We can turn them into densities. We can turn them into sizes, and we start learning about the physical properties of the star-forming regions that either are forming stars or have not yet. We're looking at this in a very unbiased manner. We're looking at their properties from a statistical standpoint, really for the first time. And so we can see all of our masses, they range from about 10 solar masses, and these guys have to be pretty close to us, almost up to 100,000 solar masses for some of these objects. So some of these are relatively large. Now, the problem is that mass depends on distance squared. So this line is basically distance squared. And all the masses are above that, but you can see that as we get farther away, all of our masses are getting bigger. So having an accurate distance constrains or is critical for determining these masses and actually understanding what's going on. From a mass and a radius, you can determine volumes, and you can also determine sizes. So after looking at these nearly 2,000 sources, our next project was to study sort of one segment of these sources in detail. And we actually studied an infrared dark cloud in the outer galaxy in Cepheus, which is, we've termed the G111 filament. So it's at a galactic longitude of 111 degrees. But the filament is this J-shaped structure right here. There's also a well-studied, well-known star-forming region right here, NGC 7538, and another one below it. But very few people have done anything with this region at all. There's a couple papers where they've done sort of pointed surveys of, oh, we found a couple bright objects. Let's just see if there's anything interesting there. And no one went much further. So what we did was we mapped this filament with the 100-meter GBT, the Green Bank telescope in West Virginia. And what helped make this possible was that they came up with a brand new instrument that has 7 pixels. So for all of you people with those 5 megapixel cameras out there, we're not there yet. But with 7 pixels, it basically allows us to take 7 times the data. And we're also, and we're able to observe ammonia, the same stuff you clean your floors with, ammonia 1,1 and 2,2, which are inversion transitions, which I could go into detail, but basically they allow us to determine the temperature of the ammonia, as well as water masers. So a maser is a laser. Basically, you can get coherent emission, but it's at microwave frequencies or wavelengths. And so that's why it's called a maser. And then we also looked at CCS, which is a carbon chain molecule that if you detect it, you know that the gas is sort of in its early phase of evolution. Star formation is just starting. Now what's nice is that at the GBT, we're looking at 100 meters, with a telescope of 100 meters, which is 10 times larger than the SMT or the CSO, but we're also looking at a wavelength that's 10 times larger. So we have the same beam size on the sky. That means we're looking at the same angular resolution in all 3 cases. So they are all directly comparable. And here's an example of our maps. Here's that BGPS map that we looked at with the different sources we were studying. But then here is the ammonia 1,1 map, and you can see it traces the dust emission very well along the entire length of the filament. And 2,2, which is harder to detect because it's coming from a warmer component of the gas, And it is also well detected through the entire section of this filament. Water masers. Along the bottom, several water masers are associated with this feature and several others along the top. And then we also happen to get HCO plus data and N2H plus data from the SMT. And the HCO plus traces the same gas, and N2H plus actually only shows up in the brightest areas. It is detected in a few more, so many of these individual sources are detected, as we did initially in our survey of this region, but they're not very bright with respect to everything else. An example of the ammonia spectra are here, and these are just 4 different of those different sources that were plotted up in those ellipses. And ammonia has 5 different components visually, but it's actually made up of 18 different components for the 1,1 line, which is the stuff that's raised a little bit. What am I trying to say? So it's up here and traced by the blue models. So the blue lines are the model fits to our spectra, and the red lines are the model fit to the 2,2 spectra, which are just lowered a little bit so you can see them. But most of our lines are very well detected along this entire filament, but not everything is very bright. There are some sections that are actually really faint. They don't have that much ammonia in them, or they could be very cold. But with those model fits, because there's so many hyperfine lines, we can actually determine kinetic temperatures, so how fast the gas is moving. We can determine excitation temperatures, which is, because the gas could have a different speed than the, not sure exactly what I'm trying to say. Can have a very high speed and have a high kinetic temperature, but because it's so rarefied, it may end up having a low excitation temperature because the molecules don't run into each other very often. And so you're not getting very much, they're not emitting very much energy out. And that would give you a low excitation temperature with a high gas temperature. So we can measure kinetic temperatures, and you can see along this entire filament, it looks fairly uniform. There's a couple spots that may be a little bit higher temperature, like this region up here, and a couple that may be a little bit cooler. But for the most part, they actually lie right around 15 Kelvin. And don't range much beyond 10 or below 10 or above 20. We can also look at the column densities, which can also be fit from that same modeling. And with the column densities, you see basically the same structure as the 1.1 millimeter emission, where you see the big chunks, and then it's sort of just clumpy in the different spots all the way up. And our column densities tend to be around 10 to the 14 particles per square centimeter. Now, column density does not take into how thick the cloud is. It's just totaling up everything and saying, this is how much I see on the plane of the sky. We also fit for the velocity structure of the filament, and that can tell us a lot about how this filament is changing, or how this filament is connected in the sky. Now, if let's say that this part of the filament was moving at a completely different speed than this part, well, we'd say that those are 2 different clouds that are just happen to be in the line of sight and appear to be connected. But in this case, we see that the velocity structure is actually very smooth, and it just slowly moves up the filament. Well, that could be that the filament is at an incline, and it's just galactic rotation that is causing that slight shift in velocity. Filament could be rotating. So there's information that we can get about how these clouds fit together from this velocity structure. Now, the last section of our analysis was not just to study the overall global morphology of this filament, but to say, okay, well, what's going on inside of these, inside of the filament? Well, at first we had done pointed observations at the centers of each of the Bolacam Galactic Plane Survey peaks. So this is one source. And we thought, okay, we're going. And then we started studying this in more detail, and we realized, well, there's more going on inside of a BGPS clump than just one thing in the center. And so if we look at sort of that 1-1 temperature map, we can now see that this source breaks up into 2. There's another source that happens in between, and this one ends up being several. So we went through and we broke the analysis up to look at different ammonia peaks. We combined information about carbon monoxide outflows, which are the red X's and the blue X's, whether it's outflow away from you or outflow toward you. The red circles indicate shocked H2 emission. So that's outflowing material from a protostar. Just increasing signal and noise from this map to this map, we were able to see more structure because the ammonia maps are significantly higher signal to noise. And if you take this down to below 30 arcsecond resolution, which our GBT maps are at, we might be able to see a lot more structure, in which case the actual core properties are associated with activity, whereas the clump properties, and clumps contain several cores, the clump properties are not necessarily showing us our activity. So conclusions from this part of the talk: from our BGPS follow-up survey, we observed about 2,000 sources, of which 80% were detected in HCO+, and about 50% in N2H+. Our multiple velocity components were really rare, which is unlike the carbon monoxide, so we're able to determine distances from this information. We have strong correlations between the integrated intensities and peak temperatures, as well as strong correlations between all of the dense gas emission and the dust emission. So we can now take those BGPS maps, say, well, we want to study in HCO+, what is the brightness of this source, and we can determine how much integration time we need in order to get a good detection. Our observed line of sight velocities follow the same galactic distribution, which is good, but they also line up preferentially on top of the areas where the CO is really strong. We're able to obtain kinematic distances for nearly half, almost 650 sources. They have median sizes of just less than a parsec, and a median distance, because again, we were combining them with infrared dark clouds that are fairly close, only at 2.5 parsecs, or kiloparsecs, actually, is actually what that's supposed to be. That's a little close. And a median mass of about 300 solar masses, using that temperature of about 20 Kelvin for our first paper. And one of the things, if we take the slope of all those masses we found and turn it into what we call a differential mass function, or a clump mass function, we get a slope of about minus 0.9, which is intermediate between the mass function of the giant molecular clouds from the CO and what we see in stars, in clusters of stars, which is what we call the saltpeter IMF. So it's interesting to see the CO is collapsing to form a slightly different distribution of clumps, which then collapses to form another slightly distribution of stars. Now, one of the first things that we learned from our G111 study was that 20 Kelvin is probably not exactly the right number. 15 Kelvin seems much more appropriate. That's the median, but also most sources lie closer to 15 Kelvin than they do either of the other sides. Our line width indicates that these filaments are not thermally supported, so the temperature inside that filament is not keeping it supported. It has to be turbulent, and that's the same thing that we found looking at all the BGPS clumps. And the clump sizes are actually fairly similar, of about half a parsec and a mass of about 200 solar masses. And we cannot find differences between the active and inactive clumps at 30 arcsecond resolution. And that's why the next step is to go to the VLA and observe the G111 filament using an interferometer, so we can get down to small scales and start to resolve out individual cores. And hopefully within the next year, the Herschel team that is studying these star-forming regions, they have a map of this same filament. And we'll be able to directly compare the dust structures with the gas structures and the dust-derived temperatures and the gas-derived temperatures, which gives us a handle on a lot more information. So that should be pretty interesting. Anyway, the next part is the astronomy education part. And with Ed, what we did was we used the light and spectroscopy concept inventory to study the teaching and learning that was taking place in classrooms across the country. Now, what is a concept inventory? It's a 26-item multiple choice test. I mean, it can range a little bit, but it's a fairly short multiple choice test that focuses on a very specific concept. So in our case, light, and it covers 5 subtopics that are commonly taught in astronomy classrooms: properties of light, luminosity, temperature, and area, Wien's law, Doppler shift, and spectroscopy. Now, in the entire study, nearly 4,000 participants took the LSCI, and we have pre-test or post-test data from them from 31 institutions, 69 classrooms all over the country, from big schools, small schools, you name it. So this is a very well-sampled study for these individual students. An example question from the LSCI is that using these 3 waves, which wave will arrive first at an orbiting satellite just above the Earth's atmosphere? Now, this question is testing, do students realize that all light travels at the same speed? So they should be answering D. But some students think that, oh, if it has a bigger amplitude, it's slower, or if this looks like it moves faster. They have misconceptions that you can actually tease out from questions like this. Here's another sample. Given the fact that we've talked about Doppler shift, we're going to use our organic voting system. So A, B, C, D. You'll have 1, 2, 3, 4. And see if you can figure this out. When I count to 3, you can put your vote up here on 3. And then we'll see if we need to do anything. So go ahead and read it. Does anyone need more time? Yeah. All right. On the count of 3, we'll vote. 1, 2, 3. Looks like everybody got it. Good job. The answer is C, because all of the 3 remaining spectra, other than the one moving at rest, should be blue shifted. So you're looking at the one that's farthest to the right. So good job. You guys are already doing better than some of the students in our class. So with all this data, what we wanted to do was ask the question, well, what can we measure about the LSCI itself? In the first paper that we authored in 2009, we studied individual classrooms. What are the learning gains that were happening in these different classrooms? And we tried to correlate it with the types of interactivity that were happening in the classroom. Well, my question was, well, since there's a lot of noise in that data, what can we learn about the LSCI? Are there bad questions on the LSCI? I mean, it had to be validated, so it's gone through a study. But now that we have 4,000 participants, what can we say about that? Is there something that's sticking out of that there might be a problem? And so we performed a classical test theory analysis to begin with on the LSCI, which gives us an item difficulty, basically the fraction of students with incorrect responses, item discrimination, how well the doing well on an item correlates with doing well on the exam, Cronbach's alpha, which is basically a measurement of how consistent the items are within each other, the gain score, which is a difference between a student's pre-test and post-test. And 2 things to note about classical test theory, though, is that the gain score is just ordinal. Just because you answered more questions we don't know how much more you know, other than that you've answered more questions correctly. And if I gave the same LSCI to this group of people versus our undergraduate students, I'm going to get different item parameters. So there are downfalls to this, but it was the first part of the study that would lead us on to other models that come after this. So we can look at the LSCI difficulty. Now these are slightly confusing to read, but basically the pre-parameters are on the x-axis and the post-parameters are on the y-axis. So in this case, we're looking at difficulty. And if we wanted an item to improve, that we've taught something, that means that we should have a higher pre-difficulty and a lower post-difficulty. So everything should be below this line. Item 21 kind of sticks out. So that's the first one that we want to look at. There's some others, like item 16 didn't change much. So there's items that we wanted to go through and check. But item 16 itself started out pretty easy and it didn't change. Maybe people were able to figure it out, but it's one of those concepts that not everybody was able to figure it out after a whole semester of instruction. So, but it's something that we'd want to look through. Looking at discriminations. In this case, you want to be above the line. You want a discrimination to improve post-test. Item 21 again. Something is not going right with this question. Doesn't mean that it's bad, but we want to study it. But for the most part, all the rest of the questions improve from pre to post. And some of them are fairly discriminating. These values above 0.5 are really good. So problem items that show up in our analysis were item 14. Item 14 is the simplest item on the LSCI. But you can say, okay, we'll throw it out. But you need something for people that are taking the pretest that they can actually answer correctly to begin with. Otherwise, you have no measurement of how they change. Item 21 has a low discrimination, and its difficulty increases from pre to post. That doesn't seem right. And item 25, it's the hardest item on the LSCI, and we think that it should be kept because you need something that brackets the top people. Did they actually achieve this level, or did they guess their way up and just get a fairly high score? And so it's a good question to bracket their full understanding. So if we look at item 21, we can actually go through it again, and we'll do the same sort of thing. I'll let you read the question, we'll vote. All right, on the count of 3, let's vote. 1, 2, 3. It's a bad question. So that was a little all over the place, and that's sort of what we were seeing from students.
What does Wayne think the right answer is?
The answer is C. It's producing a bright line spectrum. The only way to get a bright line spectrum is from a hot gas.
It's not true.
Well, you still need hot gas. But in an Astro 101 class, that's typically what's taught with Kirchhoff's laws. You have a gas that's coming from it.
What about all these?
So students are all picking hot and dense. Would you agree that that's a bright line spectrum?
No.
No. So something is still wrong. They're not getting the cool and diffuse or anything else. They can't tell the difference between these two words.
What about all your 15-degree clouds you told us in the first time?
Well, okay, yes. But it's still warm compared to the rest of it. But they're not getting confused on the hot part. They're getting confused on whether or not it's difference between dense and diffuse. So what's likely wrong with this question may actually be something that we wouldn't catch as astronomers. The jargon. Well, yeah.
It's not hard to do.
But the word diffuse may never be used in class. They may mention dense or they may mention opaque in class. And so these words may not even be in the vocabulary of the students at all by the time they take this. So it's a question that we need to study and do possibly a few focus groups and see what words would be better choices, or potentially remove the question and replace it with something that is clearer or whatnot. But it's obvious the students are not getting confused between cold and hot, because 80% of students are selecting hot. They're getting confused between dense and diffuse. So other than going through each of the individual items and trying to study them, we also wanted to say, well, what are the changes in student learning that are occurring in these classrooms? So for this, we can plot their pre-test score versus their post-test score. In the class averages, from the study in 2009, we found that almost everybody lands right in this 20 to 25% range. And you can see that it's weighted in here. But there are students that are not doing well on the exam, and they're not just marking them all wrong on purpose. They're actually falling into traps and answering misconceptions, or falling into misconceptions. And there are students that are also getting 80% on the pretest. So our students that come in aren't all just, you could say they're guessing, but their response patterns are not guessing. They're all falling for traps. They know about 25% of the material about light. But some of them know quite a bit. But after instruction, we have students that started out really low, that end up performing very well. So they're not concepts that are too hard for them to learn. And so in these classes, students are learning quite a bit. The problem is that we have students that fall below this line, which means that they are unlearning material through our class. We're hurting them. And there are some classes where the class average lies down here. That's not good. When your students know less information after a semester of instruction, that's a problem. And so doing these studies, understanding what the LSCI can measure, taking it to the next step using item response theory to hopefully get a better handle on the gains that these students are achieving in class, and really starting to see the differences in teaching techniques and how these can be implemented in the classroom is important, and it's our major next step. So our conclusions: the LSCI difficulty is very, very challenging pre-instruction, but it's well matched to the students post-instruction. They're all above 50% post. Cronbach's alpha, that reliability factor, is very high for an instrument like this. And the students are able to achieve 80% pre. So our students are not dumb when they come in. A lot of them may not know much, but there are some students in your classrooms that know a tremendous amount. We would have never have expected them as gen ed students that come from high school and act like they do in our classrooms to get this high pretest. It's just not what you'd expect from that sort of class, where you turn this around and you give this to an astronomy majors class, and you'd probably be disappointed if they're getting less than 80% in your class. But that's what these concept inventories can do, is they can help you measure what's going on in your own classroom. And understanding what that concept inventory is measuring is like characterizing your ruler. It allows you to use that to measure other things. And so this study was very enlightening to start that analysis. And I would like to thank you all for coming. So, are there any questions before we all have to leave? Yes?
How do you define the hardest and easiest question?
So, that is based off of the difficulty parameter. Let me see if I can pull up that plot. Where item difficulty, we changed it. A lot of people will use p-value, which is the percent of students that are getting it correct. But that inverts. That's saying a hard question is a 0.2 and an easy question is a 0.8. And that just seems really non-intuitive. You'd say that a hard question has to have a high value. So we flipped it around also because it matches up with our next analysis, where harder questions have higher numbers. And so it was easier to correlate cleanly. But basically, we just look at what the item value is. So to begin with, 70% of students are able to answer 14 right. And so that's why we say it was the easiest. In 25, only 8% of students are able to answer it right pretty much at any time. Yes? It's one of the only infrared dark clouds that was found in the outer galaxy, because you don't have this bright galactic emission in the outer galaxy because there's not much out there. It happened to be near a well-studied region, and I don't know, we kind of talked about it, and it seemed it's unique because it's also up for a really long time, so you can apply for time and you can get large blocks of it too. I mean, there's lots of reasons that you might want to do that rather than study something that's towards the galactic center that's up for an hour a day sort of thing. Yes?
You did a really good job. I understood. Just wanted to know, so how many arms are we seeing now that are
So from our analysis, I mean, it depends on how tightly wound they are, but we could see 4 different peaks. So you could make an argument for 4 different arms. One of the standard models currently is to use a 2-arm Milky Way, but that is not set in stone. And a lot of the work that is being done by Mark Reed, looking at parallax distances to lots of these star-forming regions, is hopefully going to help us figure that out. Because we're learning more about the rotation curve of the galaxy, more about the mass of the galaxy, but then also where all this structure is. Because if there's a really good chance that you're only going to find the most massive star-forming regions that show all of this maser emission that they're using in the spiral arms, where that gas is already the densest. So if you're finding something that happens to be in the middle of nowhere, and there's nothing else around it, something is weird, or that's going to change the model of your galaxy and move the arms in that direction, not necessarily say, oh, yep, no, we just missed something the size of Orion that's in the middle of nowhere. So in the coming years, we're going to be able to answer that question. Yes?
Can you tell me something about the environment of these 10 solar mass cores?
Environment being...
Well, do we see these 10 solar mass things just because we're close, or are they in...
all those 10 solar mass cores are really close to us.
But otherwise, they're in completely normal, what we call clouds?
So let's see. The majority of the BGPS emission looks very much like this. A lot of those cores tend to be just small things that are along other filaments that are already there. And you just see these small structures. And they may be strung along themselves. It may be just a bead of small cores. But a lot of them tend to be just these small, faint objects.
Other stars embedded in them?
We are looking at a lot of that. And that's part of what we were looking at here, is looking at what's embedded in each of these. And I forgot to mention one thing. So I mentioned the top two plots. This is our water maser plot. And this is the WISE 22 micron image. So here, this is looking at embedded protostars, more or less. And so you can see that in some of these, there are definitely embedded objects. In others, they're fairly quiescent. And even in the shocked H2 maps, there's not much evidence for anything being within a beam of where we were looking. Yet there are also protoclusters that are forming in these things. There's quite a few, or I think 3 different clusters that are forming along this filament that you can see that have very strong outflows. But other than that, the clump doesn't seem any different than its neighboring clump that has nothing in it. Any other questions? Even for a NASA sticker? Okay.
You find that, I mean, I know different time periods, and this is for your education part, that astrology comes up as a real strong point for the students that come in. Do you find that that interferes with you trying to explain to them the science, astronomy? Does that cloud the vision? Does that cloud the understanding? I know Bart Bach in his book periodically would take on this campaign to stamp that out. Do you see that?
I'm going to say yes and no, because generally their belief in pseudoscience is correlated with their belief in their horoscopes, which is basically what it is. And so it's not that they can't learn the science, but they're not willing to let go of their beliefs and actually learn what's real. And that's what's so hard about the LSCI, is that we put a lot of these misconceptions in because it's real easy to write down the answer the teachers wants. But when you see the answer that feels most comfortable to you, you're like, no, it's this one. They're going to go for it. And so it allows you to tease out some of those misconceptions. Now, with the horoscopes and it's affecting their learning, I haven't studied it myself. Stanley may be able to say something about it. She's done a little bit of some of this pseudoscience stuff. But I don't know if it stops them from getting an A in astronomy class at all. I mean, they did a study a month ago that came out in Nature where the belief in global warming versus the scientific knowledge of the person, and it was slightly anti-correlated, where people that were more likely to not believe in global warming because they were scientists given the, and that's a little disturbing. But it's that same sort of thing. Just because you have this knowledge doesn't make you successful in this type of course. But that's something that we are trying to compete against in getting them to think like scientists and realize that pseudoscience is what's controlling their lives. And if they walk around believing all the statistics that people give without taking them into context, then they're just sheep.
Any other questions for Wayne? And as I said at the beginning, thank you for coming.